In this video, we're going to talk about how we can convert a quadratic function from the standard form to vertex form. And in particular, we're going to focus on the type of quadratic functions that have leading coefficients that are not equal to 1. So in order to work with the standard form converted into a vertex form, we're still going to use a technique with completing the square. And the difference here was the leading coefficient being not equal to 1 is we're going to go ahead and factor out the leading coefficient so we can transform this type of problem into a similar form as if the leading coefficient is 1. And because of all the factoring and completing the square process going on, it's really important to keep track of what you are doing in each step and make sense of why we're doing every step throughout the process. And also it's really important to keep your work organized, whether it's bracket, parentheses. You will need multiple grouping symbols in this process. So just bear that in mind when you're watching the video and completing the process to follow along. So in part 8, we have this function f of x, and we want to convert this to the vertex form. In order to do this, the first thing we want to do, as I said earlier, is to factor out the leading coefficient. And the key is always to work with the leading coefficient to be factored out. It's less about looking for what's the greatest common factor, but using the idea of what we understand as factoring to complete this process. So whatever the leading coefficient is, we're going to take that out. In this case, the leading coefficient is 6. And when we are doing the factoring process, just like we did for completing the square, we only need the variable terms in order to complete a square. Because of this, we're going to just factor that leading coefficient out of the variable terms. And once we do that, we would have 6 times x squared minus 2x, and then we just keep the constant term, minus 2, as is. We don't have to do anything with it, but keep in mind we'll need to carry that term. We're just keeping that same term. And now to complete the square, we're just focusing on the part of x squared minus 2x. And the process is identical to what we did before when we're just working with completing the square to find x-intercepts or solving for an equation. So we're thinking about what I need to do in order to complete the square, or what does this turn into in order to complete the square. So what happens as we have learned about completing the square is we can rewrite this x squared minus 2x as part of a perfect square trinomial. And in particular, I can say this is going to be written as x minus 1 squared. And if you remember, we have this minus 1 coming from the linear coefficient minus 2, because we said as we're doing the FOIL process, if we had x minus 1 times x minus 1, if we do the first, we'll get x squared, and that's why if we had x squared as a quadratic part, we're just going to have x as a first term in the binomial. And as the inside and outside, because they are repeated binomial expressions, they will be identical. They'll become minus 1x, which give us minus 2x. That's why we always half of that linear coefficient. So that becomes minus 1. And eventually we have a plus 1. So this really comes out to be x squared minus 2x plus 1. And to complete the square, notice we have that additional plus 1 added, which we didn't have. So what we're going to do is we have to subtract that 1 away back, because while I'm writing x minus 1 squared, this is really equal to x squared minus 2x plus 1. In order to compensate for that additional plus 1 I added or highlighted over here, I'm needing to subtract it back over here. And then everything else, we just copy it down. We don't change anything about it. Now if we look at everything we have, what we want to do is to try to get rid of some of the grouping symbols. We're going to start from the bracket. So with a bracket, we have 6 to distribute into every part of the expression inside. So we really would have 6 times x minus 1 squared, and then 6 times negative 1, which becomes minus 6. Make sure you go through the distribution. and that minus 2. We just carry along. So altogether, we would have 6 times x minus 1 squared minus 8. And now that's going to be the vertex form that we're looking for. And in particular, if you want to look for the vertex from here, we know the vertex is going to be 1, negative 8. That's what we're looking for. And in order to solidify or get used to this process, we really want to practice with multiple problems just to make sure we have this understanding solid before we move on to future practices. So if we look at part B, we want to do the same thing. Whatever the leading coefficient is, here it's 3, I'm going to factor that out. And I only need to factor it out from the variable terms. So that becomes x squared plus 6x. And then we just keep the constant part. And then we want to think about if the variable terms are part of a perfect square, what would it look like? And in this case in particular, it would look like x plus 3 squared. It would become part of x plus 3 squared. Because if we were to multiply out x plus 3 times x plus 3, we would get x squared plus 3x, which is 6x, then plus 9 over here. So we already have the first two terms. The only additional term we have to take care of is the plus 9. So in order to write this perfect square, I essentially added this 9 that didn't exist. And because of this, I have to subtract it away over here. And close the bracket and bring down the plus 1 that was outside the factored part. And now if we want to put everything together, we want to go ahead and distribute the 3, that leading coefficient, back to the vertex form. Then 3 times negative 9 will be minus 27 plus 1, which is 3 times x plus 3 squared minus 26. And again, a good practice is to think about if you had the vertex form, what's going to be the vertex over here. So just as a bonus note, we have, in this case, negative 3, negative 26 being the vertex. Remember, the x-coordinate of the vertex is always the opposite of what we have in the second term of binomial, because we have x minus h in the vertex form. So we always take the opposite sign. When we had x minus 1 earlier, x equals 1 is going to be the x-coordinate. And similarly, if we have x plus 3, negative 3 is going to be the x-coordinate of the vertex. And that's how we complete the square with leading coefficient that's not equal to 1. And when we're working with this type of function, the main difference between what we did when we want to find 0, solve for x-intercepts for quadratic functions by completing the square, is I can only keep everything on the same side. I can't move terms around anymore. So everything needs to stay on the same side, and that's why we require all these grouping symbols along the way. And now for part C, we can go through the same process. If we have h of x, now the leading coefficient is negative 4. So I'm going to go ahead and factor out the negative 4. Whenever you factor out a negative sign, make sure you pay attention to the sign changes. Negative 4x squared becomes x squared in the parentheses, and negative 12x, if we factor out negative 4, becomes a positive 3x. And then we still keep the plus 5. And here, if we want to complete the square, we still want to use the same strategy as before. When I write this as part of a perfect square trinomial, this will become x plus 3 over 2 squared. And it's 3 over 2 because we know 3x comes from the repeated term of the inside and outside over here. And now if we compare what happened when we had x plus 3 over 2 squared, we should get x squared plus 3/2 x plus 3/2 x plus 9 over 4. And therefore, we had an extra term of 9/4. And this is the additional term we added by writing this whole thing as a perfect square, by completing the square. So whatever we added, we have to subtract it back, just so we know our equation is still true, and we keep the plus 5 as usual. And now putting everything together, we want to distribute the negative 4 into the bracket. That becomes x plus 3/2 squared, and negative 4 times negative 9/4 becomes a positive 9 and plus 5. So altogether, that becomes negative 4 times x plus 3 over 2 squared plus 14 as a result. Again, a good question to ask yourself is, what would be the vertex here? Here the vertex would be negative 3/2 and positive 14 in this case. Now we are moving on to this part where we involve some fractions in completeness square, and just as before when we first learned completeness square, our goal is always to keep in mind where the perfect square form would come from and what it looks like. In this case, we want to keep track of the form, and even if it has fractions, the process is still the same, so it wouldn't throw us off the track. Lastly, for part D, we want to look at this leading coefficient of negative 3. And again, you can see the number gets a little messier this time because negative 3 is not a factor of 5. So if I factor out negative 3 here, I would have x squared minus 5 over 3x. Because I'm essentially just thinking about negative 3 times what would give us positive 5x, and negative 3 times negative 5/3 x will give us that. And then don't forget the minus 4 at the end. Then we want to think about if I had negative 3 and x squared minus 5/3 x is part of a perfect square. We always start with x because x times x gives us x squared. And again, the linear coefficient here is negative 5/3. So based on what we did before, it comes from two of the same terms. So divided by 2 gives us 5 over 6 squared. And the number that we included, always come from the last. The last is really going to be the constant times itself. Here, negative 5 over 6 times negative 5 over 6 will be 25 over 6. So this is a side note. Again, that's nice to have to think about where that additional constant term comes from. It's always going to be whatever that constant you just wrote down squared because of the FOIL process. And because we added this term that didn't exist, we have to subtract it away. Subtracted by 25 over 36. And then minus 4. So now altogether, if we distribute the negative 3 through, we would have a positive 25 over 12 because we have some cancellation between 3 and 36, which becomes 12 in the denominator. And now if we want to combine them, we need to get a common denominator with the constants. So we have 25 over 12 minus here 4. If we want to get the denominator to be 12, we have to multiply 12 on both sides of the fraction. And that would give us 48 over 12. So altogether, if we put all the information here, 25 minus 48 would be minus 17 over here over 12. And if you want to find the vertex over here, we can say the vertex is 5 over 6, negative 17 over 12 over here. But if you just need the vertex form, you're done in the last step over here once we combine all the constants.